Dr. Efstratios Gavves. Welcome on stage. We hooked up your own laptop that should be working. Okay, have fun.
Thank you very much. Yeah, thank you very much for the honor and the invitation. It was very interesting actually to come here. Usually I don't talk about systems, but I actually believe it's a pivotal system in AI. So I'm going to take now the opportunity to pitch my my thoughts on the topic, and I would love to hear more from you back. So we all know about ChatGPT, diffusion models, DALL-E, Midjourney. In fact, there's a bunch of them right now. Now it's mostly recognized by the term foundation models, foundational AI. In my opinion, this demarcates the third phase of AI. Deep learning was the second. And I believe that we're going to be going from AI models to AI systems. And I would like to discuss this with you. So, the past decade has been the golden age of learning algorithms. AI existed since the 60s, there was, like in the 50s, there was like a fierce battle between connectionists and logicians on what makes a system really intelligent. At least in the last 10 years, I'm not going to say that one completely annihilated the other. No, like hybrid systems are the way to go. However, the last decade has been the decade of learning algorithms. When I did my PhD in 2008, there was exactly the types of tasks that we were focusing on. So segmentation. Back then, segmentation, you could get accuracies of 32 mean average precision, whatever, it's a type of metric, of accuracy metric, and people were excited. They thought it's like really like great accuracy, like we're really like on the right path and whatnot. In fact, Amsterdam and the Netherlands was spearheading research in this direction. Like one of the leading methods was from our university. Now we can say that we are really close to truly solving it from the academic perspective. Of course, as very correctly put before, like systems make silly mistakes still, but the methods are there. Yeah, you just need to scale it up more. We just need to put more data and more compute. So we have to improve a bit on that, but the methods are there more or less. At the same time, the last decade, we have algorithms that can narrate scenes. They take as input a picture, and they can actually describe it in the form of a caption, of a text. You got algorithms that have won the 18 times world champion Lee Sedol in the game of Go, and algorithms that even manage to solve basically protein folding. Protein folding was a computational challenge from the 60s, biannual. It was not working that greatly. They were trying via computational methods to solve protein folding, understand how proteins structure themselves in the 3D space. It was an extremely hard problem. There was no chance of solving it until DeepMind and AlphaFold was proposed. And basically they solved it, at least for the type of a challenge that was being organized. Now, what is very interesting is that all these learning algorithms, like all these successes, basically rely on the same learning algorithm, deep learning, right? Like neural networks. Like, how many times can you say that a single tool, a single algorithm, can so massively and generally address so many problems? Not many. So deep learning has brought us really a long way. And specifically, we had impressive progress in the last 10 years. So in 2014, Dirk Kingma, he was sitting next to me when he was doing his PhD. We were having these type of generations. With generative artificial models, generative adversarial models, we start getting color images with obvious artifacts, higher dimensional, not great, but definitely better than before. With engineering improvements as well as scientific improvements, the generations were getting better, and now we're really now in the regime of actually getting really good results. In 2018, we start having really believable generations. All these are fake faces, like, okay, this is sort of a toy generation, but now we can really see computers generate genuinely plausible inputs. Now with diffusion models and stable diffusion, Midjourney are models that actually rely on these. You can get even higher dimensional, even more precise. Like these tasks are now considered to be solved also from the foremost experts in the field. So in my opinion, like taking a step back, like I was working always on models. Not these models, I wasn't working with generative models. I was mostly working with computer vision, object detection, object recognition, and visual object tracking and so forth, video as well. But they're all similar, like they're like, in neighboring domains. Taking a step back, what we've been working on was on types of models, like perceptron in 58, Lenet in 98, Alex in 2012, transformers in 2018. Now we have ChatGPT, whose scale increased like significantly. And immediately after ChatGPT appeared and went public, researchers, and not even just researchers, like just curious people, started playing with it a lot. Like they were trying to combine it. They combine it with like, web parsers and other existing software systems. They made AutoGPT. Now you can actually give a command to your computer and ask like, okay, please destroy the world. And then AutoGPT will go log in online, use ChatGPT to actually converse with the websites and various search results and come up with a plan on how to destroy the world. This is a bit scary. It clearly shows how technology can be ill-used. On the other hand, it also shows that people start actually combining things, combining system components, combining AI models. So in my opinion, this actually demarcates a truly interesting, perhaps the industrial era of AI, where now we're not going to rely on single models, like one model that I just trained on my single data set and like that's it. Like it does a very specific thing, who cares? Like maybe one person or two people that actually working on exactly the same topic, and that's it. No, I think now what we're going to see is going to be more and more systems, so combination of models. What does this mean? This is what I'm going to discuss today. So who am I? I'm Efstratios Gavves. I'm associate professor at the University of Amsterdam on deep learning, ERC starting grad and VD laureate, Ellis Network of Excellence in AI Scholar, co-director of the CUVA and POPART lab with Qualcomm and Electa, as well as Netherlands Cancer Institute, and co-founder of Elegant AI. And specifically, my interests are on temporal deep learning, so specifically on how basically machines can interpret the dynamics of the world, like the temporality of the world, the interventions and the causality of the world, not just statics. Statics is basically what almost all algorithms have been doing so far. However, I believe their failures is because they cannot really understand dynamical changes and temporal patterns. Temporal deep learning addresses 4 different domains in my research. Embodied AI, so how I can basically build algorithms that are not just digital, but as in the previous talk, there is a bridge to the physical world. Causal Representation Learning, so how can I learn algorithms that they don't just learn variables, they don't just learn representations, but they learn representations that understand cause and effect in a fundamental level. Neural dynamics, which is like, okay, how do I understand what actually goes on inside the algorithms, try to interpret them, and as well how to use computer vision and AI for scientific, like solving scientific problems. Now, okay, towards systems, towards artificial general intelligence, we have the foundation models, and the premier example, the prime example of this is ChatGPT. So with ChatGPT, I'm sure, like, is anyone here that has not used ChatGPT so far? Okay, I see no hands, so this might mean that either everyone has used it or, yeah. Well, I've used it. It's amazing, right? Like, I will be brutally honest, I was not expecting it. Like, when people were talking about generalists, like generalist AI, and like, well, I thought like, what an idiot. Like, that's never gonna happen. Like, scale cannot just like magically solve problems. Now, if you ask me, has it solved like all the problems? I actually don't know. But what I do know is that when I go to ChatGPT and I start asking questions, I have like canningly, like lively conversations. Are they always true? No, ChatGPT is not always true. It does a lot of mistakes. Well, in fact, when I talk to people also, it's not always great. They also do a lot of mistakes. They also say, you know, they are telling lies. It's not like, this is not like a unique feature of ChatGPT. What makes ChatGPT remarkable is that, from my perspective, is that it actually generalizes. Like, it doesn't collapse. You know, like before, when you had a chatbot, you could figure out a way to make it say absurd things or things that are blatantly false. Here, you have to really, really try. And if you just have a casual conversation, it just works really well. Now, this is a foundation model, let's say, on text. And what I would like to do when it comes to systems and like what's the next step in my opinion and my own research is I would like to do this to pair it with a physical world together with a lot of different like complex components. So ChatGPT works with language. And in a way, language, I mean, it's a bit weird and silly to say that now, but in my opinion, language is just the first step, because language is in a way one-dimensional, at least in the type of input. We know it. You know, it's like a sort of a much smaller world than the physical world, like physical space. So with language is structured because it has evolved from human, like the human species, to be able to communicate. So it has strong internal priors, whereas in the physical world, we lack these priors. It's much harder to actually say what exactly is flat surface or what exactly is a 3D object, what is perspective, what is color. Of course, we can try to teach the machine by supervised learning. That's usually what we have been doing so far. However, this has inherent limitations. It doesn't generalize very well. It doesn't scale up. And ChatGPT has shown, if anything, that scale is all that matters. So we cannot rely anymore that much on supervision. It is crucial. It is important. It's never going to go away. For sure, not in specific applications. But if I would like to go here, if I would like to have a ChatGPT for this type of, like, you know, objects, I have to go further. To clarify here, I don't mean I want to put ChatGPT in the robots. But I would like to have a generalist algorithm that, if gone, you know, in the robot, can actually interact with the world, intervene in the world, query the world, try to understand it, try to autonomously make sense of it. So foundation models are here to stay, and you can see this by the fact that there is a Cambrian explosion of them in just 6 or 7 or 8 months or a year, whatever. It depends on when you want to start from. So you've got like Stable Diffusion, DALL-E, Mid-Journey. So these are the basic ones. And then you've got like, Elmo, Robert, Electra, Switch, UL2, ChatGPT, BARD, GPT-4, Jurassic, like whatever. Like there's a whole zoo of different models. Every company and every university makes one, which is specializing in a particular domain. And what is, in the end, like a foundation model? Well, foundation models are very large machine learning models because scale is all that matters here, right? So you cannot have scale without also computational scale and without model scale, trained on vast data at scale. So ChatGPT was trained literally on internet-level data. The idea, the objective, the hope, the desire is that these models can be adapted to a wide range of downstream tasks. So if I just train my model on internet data, and that's it, like it just does good autocompletion, nobody would care, because autocompletion is good enough already. What really makes the difference is that you can actually now do all sorts of like side tasks. Well, not side tasks that they're like less important, but you can do like just from this very basic learning objective of like predicting the next word. This is basically what ChatGPT does. You can take this model and use it for all sorts of actually very interesting and much different, in fact, types of tasks, like image captioning, instruction following, the AutoGPT that I said before, and so forth. So what we see here is an emergence of understanding, and that's the truly remarkable thing about ChatGPT, that just with a single, basically scale, like the models didn't change that much over the last 5 years. Of course, they got bigger. But they didn't really change that much, at least from a technical perspective. What really changed was the scale and the data. So just with this increase in scale, it seems we have some emergence of understanding. And with that, we have some amazing capabilities. We have true zero and few shot. I don't know if you know of the work of a segment anything model. That's an amazing model from Facebook, Meta, where basically now you can you can upload any picture. You just click on whatever you see in front of you, and it can segment it like nearly perfectly. It can segment it, even out of domain. Like whatever. Like you can actually really create some understanding from the picture, like almost perfect segmentation. It's not automatic. Like this is like with user, like the user has to click, but like it works really, really well. Prompting, so guiding, instructing the algorithm, ChatGPT, and multimodality is what is coming next. So basically how to combine image and text, image and sound, and so forth. And these are some nice results from such foundation models. Okay, in the interest of time, I'm not going to, I'm going to have some of them a bit later. So we have some elements of generalization. So for example, with ChatGPT, what we see is that it appears that you can combine almost out of the box different models, and it just works. Like with some bit, maybe some fine tuning, a little bit of training, or a little bit of like care, but it really works. Like you can actually combine wildly different models trained on wildly different like domains, and you can somehow like cook them up. So what's next? Systems of AI models. What do I mean by that? Well, from like in computer science, and you got computer operating systems, where you got like shells, compilers, the user, network, memory, file, drivers. You got various process communications. Like that is what makes an operating system, or anyways like your whole software that runs your computer. Now, in my opinion, with this Cambrian explosion of AI, we will need some form of operating system like that specializes on AI. Why? Or what for? Well, you've got multiple modalities. How am I going to combine? Like if I have a robot, if I have an autonomous car, if I have whatever, like a real complex machine in the real world that does something a bit more than like our regular dumb machines right now, they will have to combine different modalities. They have to combine image, most likely. They have to combine radars. They have to combine sound, tactile feedback, text. Like, are we going to do the training end-to-end for all of them? I don't think that's that doesn't scale. And importantly, and when it comes to industrial valorization, it's hard to actually imagine that you will somehow gather magically all this data simultaneously and have that. It has to be thus multimodal, multiple task, open world, because it's AI. AI cannot be closed world. If it's closed world, then it's academic. If you want to go to the next level of industrial usage, you want open world. Communication, so you want to be able to communicate between these models. That's actually very interesting, and how are you going to have that? Integration, interpretability, safety, and specifically if you're interested in embodied embodiment, like what I then you want also the ability to intervene on your environment. So not just like going around is not enough. You want to be able to push buttons, turn on the lights, turn off the lights. That's what you want. So you would like some sort of AI operating system for robotics minus hardware. I mean, I don't want to work with hardware myself. Of course, hardware is a key component here as well. And there are experts. I don't want to work with it because that's a huge, very complex area, which I believe actually might become easier as a matter of fact with foundation models. And very quickly, I will go through these some of these topics with some recent works of mine. So in terms of causality, a few months, 2 months ago, we had a series of papers in iClear, ICML, so International Conference on Learning Representations and Machine Learning, on uncertainty in artificial intelligence in the last 2-3 years on spearheading causal representation learning. That's like a new domain. Usually deep learning learns representationless features, that everything is mixed up. There is no interpretability. Every dimension can be anything. With causal representation learning, you want every subset of dimensions to correspond on one thing, on one object. And you want this to be autonomously learned. I don't want to say that this is a phone. I want the machine to understand itself from navigating the world and interacting with the world, what objects are. And based on these interactions, I want it to learn its own internal representations of the world. So with this, we're learning by maximizing cause and effect, predictive accuracies. The causes and effects are unknown. Everything has to be learned completely from scratch. What we're given only is whether we're in an environment that we can navigate and intervene up on. With that, we can have counterfactual reasoning or making hypotheticals, like what ifs. Okay, in the interest of time, I will skip that. Also, another interesting work that is going to be presented in 25 days in ICV, the International Conference on Computer Vision, on open vocabulary video instance segmentation. So far, all algorithms, segmentation algorithms, have been focusing on a priori known categories. I know my 20 classes, like car, bicycle, whatever, and then I want to recognize them and segment them. What we propose as the future is segmenting, classifying, and tracking objects from arbitrary categories, whatever you can think of. Just put in a word, and then the computer should be able to automatically understand what you're talking about and localize it. And we actually managed to make this work. We're releasing an LVIS, it's called LVVIS video dataset with large vocabulary pixel level annotations. So yeah, in an academic setting, we cannot have a truly open vocabulary where you can think of, like that, you cannot also evaluate. Instead, what we do is we have a very, very large vocabulary, which is basically like having an open vocabulary one. And of course, at test time, you're not supposed to, you cannot see the words. With this model, the model can recognize centipedes or logs, like tree logs, telephones, key cards, whatever. The model has never seen these objects before. It's like the first time that it sees these objects. However, it managed to recognize them. In fact, because of how we combine with other foundation models. So CLIP is a vision text foundation model. And we leverage this. And temporal self-supervision on how to recognize objects completely in an unsupervised way just by taking into account the temporality and what it means, the consistency that you have through time. And last, work that has not been yet like submitted. It's like ongoing work, but I find it extremely interesting because it's different, like it's a paradigm shift in the way neural networks and foundation models would work. We call them mechanistic neural networks. So normal neural networks always output numbers, always numbers, right? Like your activations, your features, everything are vectors, tensors, whatever. Like always be numbers. In this work, our neural networks actually return equations in abstract and theoretical form. So basically, you can put like any input from picture of a horse to a time series, and then the neural network will derive an equation, as in symbolic, that basically explains the input and makes a prediction thereafter. And why I think it's important, because with this we can have interpretability. If you have an equation, it means, well, not only you can use eons long knowledge on differential equations and functional analysis, but you can also do a perturbation analysis. You can actually play with the terms here and then see what happens in terms of recognition. You can try to plot it out and understand what's going on in the black box. So yeah, we're going to have very soon with the University of Amsterdam a very big proposal, like university level proposal on Foundation AI Amsterdam, to study the science of foundation models. And part of that is with ICAI, which is Industry Academic Research Labs. I am leading Qualcomm and Lecta, Kuva and Popart Lab, respectively, also with the Netherlands Cancer Institute. But you know, like we're open for more. If you're interested in like such partnerships, let me know. Thank you very much.
Efstratios Gavves.